black out, you know. And suddenly, my phone started charging. It's out of charge. It was just crazy.
What a little slip for a girl. Well, I know it sounds like something supernatural, but what I want to tell you is, it's scientifically reasonable. It was actually done by me. Let me tell you what happened. Basically, BioDaily belongs to a larger company in Shenzhen named GBSC. Our scientists have developed a device named BIOT, which accidentally charges the poor girl's phone. And our story began with the Internet of Things, or IoT. Basically, it refers to the billions of physical devices that are connecting and sharing data around the world. With its omnipotent powers, we can expect IoT playing a major role, from maintaining the optimum humidity in the house to impeding the progress of global warming. And in the foreseeable 2030, there will be 125 billion IoT devices. Every second, 127 devices are being connected to the network. Yeah, this sounds promising. How to power billions of devices is a major issue. Currently, most IoT devices are supported by lithium and primary batteries, which are limited by lifespan and ecological impact. And it will be even worse when they need to be replaced in some remote areas. Some solutions like solar energy or heat energy have emerged. They harvest energy from the surrounding directly, but they can't be used everywhere. You need sun for solar energy. In this case, we need a solution that's environmentally friendly, self-sustained, and highly adaptive. So, is there such an ideal energy source? Yes, our inspiration came from the discernible humidity in Shenzhen. Throughout the whole year, the humidity of Shenzhen remains above 70%. And over 70% of the globe has humidity that's higher than 50%. It means that those invisible water molecules floating in the air could be an abundant energy source. Then, how can humidity be harvested? Now, please let me introduce our product, BIOT. Biotechnology-driven Internet of Things. In a nutshell, BIOT is an electric generator that utilizes a thin film of protein nanowires to harvest energy from moisture in the air, and it has great potential in IoT. The film is even smaller than a fingernail, but it can swiftly produce voltage up to 0.35 volts and currents of around 0.5 milliamp. The battery is stable in different conditions with various relative humidity and pH, even in high temperature. Besides, the protein nanowires are biodegradable. So where are these protein nanowires? The core of our BIOS is electrically conductive protein nanowire, that is EPNs. And they are originally produced from G-cell resins. And we follow a previous research to make E. coli being able to express these EPNs. I'll explain how the energy is produced. First of all, as the graph shows, the nanowires contain lots of carboxyl groups. And we assume that the more water molecules enter the film, the more carboxyl groups will be ionized, forming hydrogen ions. An ionization gradient will form following the moisture gradient. And hydrogen ions diffuse from the top to the bottom. The diffusion results in a positive charge accumulation at the bottom and a negative background at the top, creating an electric field. To develop our products, we did a lot of work, and our scientist Yomi will introduce it to you.
Our project is mainly divided into 4 parts. Firstly, bioproduction. Build genetic circuits for nanowire production and BIOT fabrication. Secondly, reduce cost. High efficiency production of protein nanowires for large-scale application. Thirdly, improve efficiency. Protein engineering to improve the power efficiency. Fourthly, realizing the full potential. Design hardware to harness the power of ambient environment.
To begin with, this is the gene expression circuit of BIOT. To express BIOT nanowires in E. coli, we need such a gene circuit. It's mainly composed of 2 parts. The first part is the protein monomer. We fuse the signal peptide to the N-terminus of the protein monomer, which can help the protein to be secreted outside of the cell membrane. We verified that BIOT's protein monomer was sequentially expressed in the cell by Western blot. The second part is the type 4 secretion system. It is a secreted protein machine distributed on the cell membrane, which is used to assemble BIOT's protein monomers into nanowires that can be up to 20 microns in length. Before transferring type 4 secretion system to E. coli top 10, we had to remove the type 1 system. If the two systems were all present, the assembly of the EPN will be affected. FIMA was the key gene in the original type 1 system, so we got rid of it with CRISPR and the donor DNA as template. From the graph, we can see that the fragment without FIMA is obviously shorter than the one from wild-type strain. Finally, we introduced the constructed expression plasmid into the FIMA knockout E. coli, and the BIOT nanowires can be successfully expressed on the membrane. Then, our next task is how to obtain and purify the nanowires from the cell membrane. The whole procedure included cell cultivation, nanowire blending, nanowire filtration, and concentration measurements. It is recorded in the form of a video for future reference. You can look it up on our wiki. The final concentration of protein solution was roughly around 200 to 400 micrograms per microliters. Fabrication and measurements. We made a battery using the following method. As you can see from the picture, it is the basic module of BIOT. The gold positive electrode at the bottom is larger so that EPN can be positioned on it, and the tiny circular carbon piece works as a negative electrode on the top. After arduous experiments lasting for nearly 2 months, finally, under 60% relative humidity, we obtained a stable output voltage of roughly 0.35 volts from a single module. The current fluctuated from 0.2 milliamperes to 2 milliamperes. Additionally, to find the optimum relative humidity for the battery to function, we did measurements with different relative humidities. The optimum RH was roughly at 40 to 50%, where the voltage rises to about 0.42 volts. We've successfully realized the power generation, but that's not enough. What we aim at was to make differences and release the full potential of BIOT. Optimization. First, cost matters. We first targeted the RBSs of the Type 4 EPN's assembly system to increase number of Type 4 secretion machine to optimize the production of EPNs, therefore lowering the cost. As shown in the figure, there are mainly 3 RBS, which are RBS of half B, half M, and PPDA. We originally planned to create a library for each RBS, then randomly combine them to find the optimum combination. So we used RBS calculator from Sal's lab, obtaining 9 more mutated sequences with various strands for each. But with 10 sequences for each of the 3 RBS, there are 1,000 possibilities. Therefore, we would need to spend 250 days on purification and only purification. Thus, frustratingly, we were forced to reduce the size of our RBS library down to 3 × 2 × 3. Due to time constraint, we only managed to successfully introduce 6 combinations out of the 18 into our BIOT wild-type strain, but we still obtained some optimistic results at the end. As the table and the graph shows, with optimum mutation, RBS for the productivity was successfully increased by 34.1%. Second, power efficiency matters. We used protein engineering technology to modify the protein monomers of the EPN, hoping to increase its voltage level. One of the perspectives we considered was the number of carboxyl groups on nanowires. We established mathematical models to explore the relationship between the number of carboxylic group and the output voltage. As you can see in the model, when the humidity is at the same level, the potential is proportional to the number of carboxyl groups. By increasing the number of carboxyl groups on the EPN monomers, we can theoretically improve the potential of the basic BIOT module. To verify our ideas, we designed the 16 mutants of the EPN genes to increase the number of carboxyl groups which reacted with water molecule to form hydrogen ions. We made it by replacing 1 to 4 amino acid in the non-conservative region with aspartic acid or glutamic acid. That's because these 2 amino acids both have 2 carboxyl groups. The amino acid we choose to replace had similar structures to them, according to our research. Another design we considered was the diameter of the nanopores. By decreasing the diameter, it becomes harder for the water molecule to pass through the nanopores. It will lead to greater water potential gradients as reported from the work published on Nature. Through our research, we found mutation design which made the diameter decrease from 3 nanometers to 1.5 nanometers. Meanwhile, we used Swiss model to predict the structure of every mutant to examine whether the mutation affects the structure dramatically. The DMSD value of each mutated protein model was calculated using PyMol. The smaller the value is, the more similar they are. The results were all below 0.03, which confirmed that our design would work successfully. Then we clone, transform the purity of the mutant, and test their performances. From the charts of the output voltage of different mutated proteins, we can see that the 4A mutant gives a rather ideal result. With the voltage increased by 46%, it reaches 0.51 volts compared to the original 0.35 volts. It's definitely an essential step in our project. The output of the thinner mutant thin was 0.47 volts, which increased from the original voltage by 34.3%. It means that the two designs both work as expected. Since there's an obvious increased trend from 1A to 4A and thin, we did repetitive measurement with these 5 mutated proteins. Surprisingly, the difference was narrowed, but the result was enhanced generally. We admit that the output voltage mutated protein is still unstable, and the reason behind it needs further analysis. But anyway, it provides a new idea for future study. Hardware design. To test whether our product could be utilized in reality, we did some further design on the hardware. We firstly connected more than one module in series. At first, we only made a board that can be used to connect multiple batteries in series. With the design copper sheet structure on top of it, using this board, we can easily connect the multiple batteries in series. As seen in the video, and with 4 of them, we managed to increase the output voltage to 1.6 volts. It proved that it could work, which means that it is going to work with 5 of them, 6 of them, and etc. We calculate the theoretical output power of BIOT, connecting a series through a simple mathematical models. And the value can reach a maximum value of 1 kilowatts per cubic meters. This value is theoretically higher than the existing solar cell based on solar power, because the drawback of solar cells is that, unlike our BIOS, they cannot be superimposed on the vertical axis, which limits the maximum output power of the solar cell. In order to better stabilize the output power of BIOT, we decided to add a PMIC module into the circuit. Although we verified that the output could maintain at the same level for more than 5 days, there were still slight fluctuations. In our designs, PMIC will temporarily store BIOS output power through its power management chip and then achieve stable output, which will further enable BIOS to meet the needs of more scenarios.
After achieving several goals in our experiments, we began to pursue real commercialization. To this end, we have made a lot of efforts, including market research, writing business plans, and cooperation. The first question we faced was, where is our market? In order to solve this problem, we attended the 40th International IoT Exhibition in Shenzhen and interviewed several tech companies. Through investigation, we found one current industry pain point is the power supply difficulties, which motivate us to design our product that caters IoT markets of power supply in specific settings. To understand the public's attitude to the application of BIoT in real life, we conducted a survey facing the public and received about 500 valid questionnaires from the people of various ages, residential areas, and education levels. The conclusion was that a lot of consumers held a positive attitude toward our product, which implies a great potential market for BIoT. However, some concerns about the safety issues still existed. So, when we promote the products, we should emphasize that our products are safe and environmentally friendly. After targeting our specific market, we began to seek business partners so as to evaluate our project from a business aspect. Thus, we came up with a thorough business plan for BIOT. In the business plan, we defined our product as a new non-polluting biomaterial that used humidity energy to solve the power supply problem of the existing small IoT terminal machinery. We also included the analysis of the pain point of the market of power supply. Meanwhile, compared our own product with other competitors, analyzing the advantage and disadvantage of them. Additionally, a detailed business model was built. In this part, we carefully consider our potential partners, resources, and customers, as well as the feasible ways to communicate, promote, and profit. For the final improvements to our business plan, we interviewed 2 experts engaged in the investment and modified our BP to make it perfect. After the accomplishment of our BP, we contacted Huawei to seek possible cooperation. After introducing our project's main idea, the company representatives were very keen on learning more about the details of our nanowire protein batteries. And they claimed that they were very impressed by what we already had accomplished by that time. However, as a group of critical experts, they provided a few points that we could enhance, and we are currently dealing with those problems to further improve our project. Here is a review of the entrepreneurship and integrated human practice of our team. To research on current need for the Internet of Things market, we began our human practice by coming up with a thorough business plan after market research. And during our discussions with professionals, we confirmed our experience goals. We sought advice from experts in academics and business to revise our plans for future applications in business. Overall, our integrated human practice centered around the IoT market, and our project also benefit from this integrated process. In terms of science communication, we first created a wonderful role-playing game about CRISPR technology, and then tried to put it on the internet for the public to play. Secondly, we made a video about synthetic biology and uploaded it to the video website Bilibili, a popular Chinese online platform. Thirdly, we held a teaching activity in the Bluefire Lab.
Now let me briefly summarize our project. Throughout the whole summer, we have successfully designed a high-performance bio-battery that's driven by moisture in the air and increased its productivity and power efficiency using synthetic biology. We have successfully conducted several activities to open up our commercial road. And as far as we know, this will be the first time that biotechnology is applied in the field of IoT. With BIOT, we can see a promising, optimistic, and bright future where billions of IoT devices connecting the whole world. And finally, here's our attribution. Here's the end. See you in the poster session.